Hi, I am Philipp Ladwig. I would like to speak about our low-cost pipeline that is capable of removing virtually a head-mounted display for immersive telepresence settings. What is our motivation behind our work? Realistic face-to-face conversations are not possible in VR yet. The problem is that the face is covered by an HMD. Ordinary video telephony would bring no added value here, and even traditional face tracking methods cannot be used for driving an avatar. Removing the head-mounted display is a relative new area of research, and there are only a few related works. The first works focus on face tracking beneath an HMD and uses generic avatars. Since 2018, personal avatars in combination with a face tracking HMD are subject of research. Especially these two works demonstrate highly realistic three-dimensional personal avatars. The color images here show the 3D avatars from the pipeline by Wyatt et al. They use an expensive camera setting for the initial face capture with 40 cameras pointing from different angles to the face. Creating the head model, training the deep neural networks, and also executing the final reconstruction pipeline requires a significant amount of hardware. We achieve not that high quality and expressiveness as the works of Lombardi and Wyatt et al. As you can see here, this is a video of our system, but our pipeline only requires a fraction of hardware, training time and inference, as well as costs compared to Lombardi and Wyatt et al. Our system tries to figure out how far we can get with just commodity and low-cost hardware today. In this presentation, I provide details to our two main contributions. First, a low-cost face tracking system for HMDs, and second, an end-to-end low-cost reconstruction pipeline of a user's face as a textured depth map that can be driven by our HMD face tracking system. I'll start with our face tracking HMD. As you can see here, we printed a mount for a camera that is attached to the front of an HTC Vive Pro. We use cameras that are actually intended for flying with RC drones for first-person views. These cameras are perfect for this application because they are small, cheap, have wide-angle lenses, and have sufficient quality and resolution for image processing. Moreover, they can be easily modified in order to see only infrared light. As you can see in the images, we use 4 infrared LEDs for illuminating the mouth area. Eye tracking is performed by the HTC Vive Pro Eye. The system reports reliable gaze position, however, it is not capable of reporting information about the position of the eyebrows. In order to get this information, we attached 2 additional cameras inside the HMD. Unfortunately, we experienced problems with the combination of the infrared LEDs for the illumination of the eyes by the Vive eye tracking and our cameras. The infrared LEDs of the Vive's eye tracking are driven by impulse width modulation and therefore produces image artifacts in our drone camera streams. Our solution was to craft our own LED rings with small infrared LEDs which have the same wavelength such as the original Vive eye tracking LEDs. Production costs of one ring is less than $3 US. We glued them over the original eye tracking LED rings of the Vive, and we've got eye tracking and clear images of the eyebrows. These are the images we get from our cameras. Our goal is to track landmarks from the face in order to drive an avatar. So, how to get landmarks out of these images? The tracking of the mouth region was a challenge because any conventional face tracking fails when the upper face area is covered. For example, we tried the real-time tracking of D-lib and the facial alignment network by Bullet and Tsimiropoulos, but we were not able to get tracking data out of these steep angles with the half of the face covered. However, we discovered that the fan, the facial alignment network, works from this steep angle without an HMD. It produces reliable tracking data. Now, our idea was to train our own lower face tracking solution as a convolutional neural network. To get labeled data from the lower half of the face, we just removed the upper half of the face and used these cropped images to train our CNN. We did some experiments with our label data and fed it to different CNN architectures. We created a CNN based on stacked hourglass networks by Nero et al., but we have had problems to achieve real-time frame rates such as 30 Hz, despite the position estimation of the landmarks was quite good. We end up with a simple and fast architecture, as can be seen here in the figure. This lean architecture, compared to a stacked hourglass, is capable of real-time frame rates. For training the CNN for a person, we need around 5 minutes of recording of the full face to get good results with an HMD as shown here in the video. Our eyebrow tracking is much easier than the CNN. We turn the HMC streams into a binary image representation, and the threshold has to be set to a value that produces images where the eyebrows is in contrast to the skin. This way we can detect the transition between skin and eyebrow in the binary image in order to track the relative positions of the eyebrow. In combination with the Vive Pro eye tracking that reports gaze and eye openness data, we can extract 70 landmarks with our face tracking HMD with 30 Hz. We can track the face, but we also want to drive a personal avatar. So the question is how? We tried to apply these landmarks to blend shapes of a 3D model. We created different avatars with photogrammetry or as 3D morphable models and used generic blend shapes, but the results were not satisfactory. The facial animation looks not personal and rather uncanny. A further option would be to ask a 3D artist to fit and register personal blend shapes in order to create more authentic animations, but this would not comply with our goal to create a low-cost pipeline. This means an end-to-end solution is strongly preferred. The solution of an end-to-end learning system which could create authentic face reconstructions would be an approach based on generative adversarial networks. Again, can learn so-called image-to-image translation. For example, it learns the meaning of the colors and structure in the map on the left and can translate them into satellite images of streets as on the right shown. The architecture of our GAN is based on the Pix-to-Pix scan by Isola et al. Similar to Isola et al., we employ an image-to-image translation between the face tracking data from our HMD and the real RGB images of a person. In order to achieve our goal of 3-dimensional avatars, we have extended the original approach of Isola et al. By an additional fourth channel, a depth channel. We have chosen this 3-dimensional representation because neural nets can learn and process more easily depth maps compared to meshes or voxels. Have in mind that we want to achieve real-time frame rates. All these data must be captured in an initial step. We built a helmet mount with an RGBD camera that ensures that only relevant data is included in the training dataset. These data are images that show the face always at the same distance from the sensor without rotation or tilting in order to minimize the variance in the dataset. After the images have been taken with the helmet mount, the images are prepared for the training in an automated step. First, the images are cropped based on the position of the face. Since we also record a depth image, we can accordingly crop this as well. For the training, it is necessary that we create landmarks to let our GAN learn the image-to-image translation. We use the facial alignment network, FAN, of Bullet and Tsimiropoulos again. Note that this network already delivers for us the landmarks for our lower face tracking CNN from the steep camera angle. This means the detected landmarks are at the same positions in the face. During the recording, the person speaks 20 phonetically balanced sentences and shows a variety of facial expressions so that these can be included in the dataset for training and learned by our GAN. On average, about 1,000 RGBD images are taken with the helmet mount to achieve a good reconstruction of the person. The recording process takes about 10 to 15 minutes. Now we can give the dataset to the GAN, and this learns the relations between the face tracking data on the left and the given RGBD images on the right. The training process takes about 16 to 20 hours and can be conducted on an ordinary gaming PC. After training, we can start the real-time reconstruction process with the HMD. This video shows our system with synchronized outputs of different stages. These two streams show what the cameras see in the HMD and the according real-time tracking results. In combination with the Vive eye tracking, we can combine the tracking results to an image of facial landmarks. This landmark image is passed to the trained generator module of our GAN that produces in real time this color image and also this depth map. We combine color and depth map for a real-time visualization. That is the final output and could be used in a Telepresence application. The crux of a good face reconstruction in our pipeline is an initial calibration step. The raw facial landmarks from our head tracking HMD, framed here, are very different to the actual landmarks which were initially created, framed here in orange, during the capture process with the RGBD camera attached to the wooden helmet mount. This means we have to create a correspondence between the landmarks from the trained dataset and the real-time landmarks from our HMD. To realize this, we calibrate our system with a neutral pose by mapping the raw landmarks to the actual real landmarks of a neutral pose that is part of the dataset. The person on the HMD has to make a neutral face, and as soon as the mapping starts, the reconstruction on the left is much better. A further improvement for the quality is a landmark cage, here framed in orange. The gray areas indicate all positions where landmarks of the training set were located, because the GAN does not learn how the real face looks when landmarks are outside this area. We limit the landmarks to known positions, because otherwise the reconstruction quality can decrease dramatically. We experienced some uncanny reconstructions without the cage. Here are some stills for direct comparison. The first column shows the calibrated landmarks from the HMD, and next to it is the generated avatar face in color, generated from our GAN. The third column shows a ground truth image. They are real images taken by the RGBD camera and the helmet mount, and were made while the facial expression was held and the face tracking HMD was taken off and the helmet mount was put on to take the picture. This way we are able to produce comparable results. Column 4 and 5 depicts metrics for comparing the results of the color images and visualizes differences. Column 6 shows the error of the ground truth depth and the corresponding GAN output. The error in the face area is mainly lower than 5 mm. The last columns visualize the combination of color and depth. Here are 3 more examples. We have observed that our system sometimes renders the eyes a bit too closed, for example here, and we think these are problems due to our own crafted LED rings and results from interference with the eye tracking of the HTC Vive. Another problem is that the GAN cannot generate expressions that were not learned, and sometimes, despite we used the cage, the user can generate an unknown expression for the GAN, which lead to image artifacts. Also, glasses lead to image artifacts due to failed depth capture, as can be seen here in the middle and on the right. Our system scales well to other persons. The entire capture process of training data for the GAN and the lower face CNN is about 15 to 20 minutes in sum. Training takes about 16 to 20 hours, regardless of the shape of the face. The entire process is automatic and no manual adaptations such as adding landmarks or artistic interventions are necessary. There are many possible ways to go next. The reconstruction of the GAN is quite fast, with 1 millisecond for a squared RGBD image of 246 pixels and around 20 milliseconds for a 512 pixel sized image. So it would be possible to learn and reconstruct the face from different angles simultaneously to get a more comprehensive reconstruction of the head. 2 more important points are the increase of facial expressiveness and the possibility for lip synchronization for speech. A higher expressiveness can be achieved with using more landmarks, which would be also beneficial for a better lip synchronization. However, lip reconstruction in our current pipeline is limited to 30 Hz, as our cameras are limited to this frame rate. Past research has shown that 30 Hz could be too slow for a faithful lip reconstruction, so we considered to use the audio signal. We plan to employ another adversarial approach with an additional discriminator in our pipeline in order to learn the correspondence between lips and audio. Our very first experiments, based on a recent paper by Pech et al., is promising, as this video with sound shows. Glue the sheet to the dark blue background. It's easy to tell the depth of a well. Our proposed system is unique in the way how it combines low-cost hardware, neural nets, and an end-to-end solution for 3-dimensional real-time reconstruction of a face that is covered by an HMD. In this presentation, we answer the question how far we get with inexpensive hardware and also open source software for a potential immersive telepresence application. As we think our system could be useful in a variety of applications, we made the source code available at GitHub. Thank you for listening, and if you have questions, please let me know.